came up with this theory when trying to discover a solution to what's called the binding problem in consciousness. And this is that if you, for example, when you see a visual scene, I can look out the window, I can see trees blowing in the wind, lots of different textures, colors, shapes, orientation of lines. All of these features are encoded in different parts of your brain. There's nowhere, if you look at the neurons of the brain, where those features come together to make a tree. Everything's dissected, and some of it, the colors of the leaves will be off in one part of the brain and their shape will be in another. You can still process that information to generate a response such as there's a tree out there. But it doesn't seem to make sense with our conscious experience where all of it comes together, all of the information is brought together in a single conscious percept of, say, a tree. And it's been a big puzzle. Where is that coming together of all of the information? And there's lots of theories to try to explain it, and none of them, I think, adequately account for it. But it occurred to me that there may be a very simple explanation. Every time a neuron fires, it involves the motion of ions. I mentioned before, motion of ions or ions are electric charged, and any moving charge will generate a magnetic field, an electromagnetic field. This means that the brain, that all of the neurons, the 100 billion neurons, when they're firing all the time, when you're looking at a tree or anything else, they're generating lots of, if you like, pulses of electromagnetic information into the brain. All of those pulses then kind of overlap and join up to become the brain's electromagnetic field, which is then detected by the techniques that we know about already. EEG, discovered over 100 years ago, that you can detect the brain's electrical field by putting electrodes on the skull. And it's a highly complex electrical structure, as you would expect, because it's generated by the firing of 100 billion neurons. And then the technique of MEG, magnetoencephalography, has been used to detect the magnetic field of the brain, which is also a highly complex structure that is highly dynamic. So we know that the brain has an electromagnetic field. What we know about fields is that they, by their nature, unify information. They are, if you describe an electromagnetic field quantum mechanically, you can describe it as a single equation, a single Schrodinger equation, which will describe all of the features of that field. It can be brought into a single equation. And that means that all of the information is unified in the brain's electromagnetic field. If you could kind of jump onto a photon in the electromagnetic field, it wouldn't matter which way you jumped, you'd meet the same information because the information is overlapping in all of the regions of the brain. And the total brain electromagnetic field has the same physical unity as, say, a single photon or a single electron. It's physically unified. So this is where all of the information in the brain comes together. So it occurred to me that that makes sense as a way of explaining the binding problem. That consciousness may simply be the brain's electromagnetic field. It's where all of the information comes together. And it occurred to me that there was several predictions of the theory. One is, because we know electromagnetic fields come in waves, like the waves of the sea. Electromagnetic fields have this wave-like character. And that means that they have a property called interference. And that is, if the peak of one wave meets the trough of another wave, then they cancel each other out. So you get no wave. You can see this if you throw well, let's go on one more step. Secondly, if the peak of one wave meets the peak of another, then they reinforce each other. And these two features are called interference. One is called constructive interference, where the waves meet and they reinforce each other. And the other is destructive interference, where the peak of one meets the trough of another and they cancel each other out. These features of waves, we know they were first discovered for light. We know it happens in water. You throw two pebbles in a still pond and you can see where the waves overlap and they Sometimes in some places they'll form bigger waves, in other places they'll cancel each other out. It's a feature of waves. If consciousness is a wave, then we would expect that there would be certain features of electromagnetic field information that will have wave-like character. For example, they should show interference. Now, if that's the case, then we would expect that if a number of neurons are firing asynchronously, so neurons can fire synchronously, in which they're firing at the same time, and if they're firing synchronously, then they will have constructive interference. So their amplitudes will multiply, will be additive really, rather than multiplicative. Then the net field will be much greater. If neurons fire asynchronously, then mostly they're going to cancel each other out. So that made a clear prediction about consciousness. For conscious information, the neurons have to fire synchronously. They have to be firing at the same time, firing in step. And that would then generate an electromagnetic field pulse, if you like, that goes off into the brain and becomes our conscious thoughts. So the prediction of that would be that conscious information we are conscious of, should be associated with neurons that are firing synchronously. That that prediction of the theory has been demonstrated in thousands, tens of thousands of experiments that show that synchronous firing of neurons is the best correlate we have for consciousness. So, for example, when you are not conscious of something, say I wear glasses, I often take them off, and then I can't find them. And I could be looking somewhere on my desk, and I don't see them, even though they're on my desk. And that means that if my glasses are on my desk and looking at my desk, the information registering my glasses is entering my brain, but I'm not conscious of it. And then there comes a moment you say, ha, there they are. And you're staring at the same information, that same information that a moment ago you were unconscious of, your glasses, you're now conscious of. Now, there have been lots of experiments in many, many systems which look at then what is the difference between information that is unconscious in the brain, you're not conscious of, and information that then becomes conscious. And the difference is that when the information is, say, neurons that are reporting my glasses, when I'm not conscious of them, the neurons are firing asynchronously. When I become conscious of them, they fire at the same rates, the same neurons fire. The only thing that happens is they start firing synchronously. And then we become conscious of the information, because when they're firing synchronously, they fire the information off into the electromagnetic field and we become conscious of it. So that prediction of the theory is fully borne out by thousands of experiments. More recently, there's another prediction of the theory, which is very important, and that is that the information in the brain's electromagnetic field, which is our conscious mind, according to the theory, has to influence neurons. Because we talk about, I can talk about the tree, it's in my conscious mind and I can talk about it, which means that information has to influence neuron firing. So although there was evidence for that when I first proposed the theory about 20 years ago, the evidence was slim. But in the last decade or so, there's been lots of evidence for neurons being sensitive to weak electromagnetic fields, the kind of electromagnetic fields that the brain itself generates. So, for example, in Christoph Koch's laboratory in California, he demonstrated that very weak electromagnetic fields will change neuron firing patterns in brain slices. And Michael McCormack, working in another US laboratory, demonstrated similar, made findings for a completely different system, but again showing that weak electromagnetic fields influence neuron firing. So then you have a loop of information. So the neuron firing generates the electromagnetic field of the brain, that is our conscious mind. And now we can clearly say that there's strong evidence that electromagnetic field information in our brain will push and pull on our neurons to actually make them fire or inhibit them from firing. So in other words, it has a causal influence on neural firing. And this, in the CEMI field theory, is, I believe, what our will is. What we call free will, it's the influence of the brain's electromagnetic field on neural firing to make us do things like lift my hand up at the moment, which I do consciously. Those conscious actions that we perform all the time, I'm doing that consciously, have been driven by the electromagnetic field in our brain. All the other stuff we do, like when I'm talking, although my hands are down here, often my hands are moving when I talk and I'm not conscious of them. Those kind of things are driven by our neuronal mind. And most of what the brain does is probably done through the wires of the brain, through the neurons, exactly as neurophysiologists believe the brain works. And this neuronal firing is certainly responsible for most of what happens in the brain. But that trickle of information which goes through our conscious mind and is responsible for our conscious thoughts and becomes the person we are, that, I claim, is actually the brain's electromagnetic field. It's generated by the brain neural firing, and it influences neural firing. And that is the loop of information that goes through our conscious mind.